In this lecture, we study metric spaces. First, we introduce the notion of distance and we define distance functions. Then we define metric spaces. So let us start with the notion of distance. So distance function. Distance functions. So let us start with a non-empty set X. So suppose X is a non-empty set. Let's draw a picture. Suppose this is X and so this is X. So let us take 2 points. Consider X comma Y belongs to X, so that is, suppose X is here and Y is here. So any 2 points. So now the question is, what is the notion of distance? So let me write the question. What is the notion of distance between 2 points? Or more precisely, what is the distance? What is the notion of distance of Y from X? So basically what we do, we assign a real number. We assign a real number denoted by dx comma y to this order pair x comma y, and this is real. So we assign this real number to x comma y from x, or you may say the ordered pair x comma y belongs to x cross x, and call this as distance and call the distance of y from x. So this is x and this is y. So this is so we put an arrow and this is dx comma y. Okay. So we put an arrow to mean that this is dx comma y. This is the distance of y from x, and this satisfies which satisfies so-called a few axioms of distances. Okay, so-called axioms of distances. So what are the axioms? So axiom 1, this is, so d x comma y, this is always non-negative. So that is, this is greater than or equal to 0 for all x comma y belongs to x. And equality holds. Equality holds. That is dx comma y, this is equal to 0. That is, this is equal to 0. So if and only if x equal to y. So the distance from a point to itself is 0, and when distance is 0, then distance between x and y is 0, then 2 points must be identical. So this is first axiom, and axiom 2, it says that so the distance of y from x, that is dx comma y, is equal to the distance of x from y. So that is y comma x dx, y comma x. This is true for all x comma y belongs to x. Okay, so that is if this is the distance dxy is the distance from distance of y from x, and suppose this is the distance of x from y, that is denoted by dy comma x, then they are equal. Okay, so these two quantities are equal, and this happens for all x comma y in the set x. And axiom 3, it says that dx comma y is less or equal to dx comma z plus dz comma y for all x comma y comma z belongs to x. And this is so-called triangle inequality. And geometrically, so suppose this is a triangle with vertices at the points x, y, and z. So suppose this is triangle, and vertices are x, y, z. So this is x, this is y, this is z. So the length of the side of this triangle, length of the side, this is equal to dx comma y, and also this is same as by axiom 2, this is same as dy comma x. And similarly, this is the length of this side with endpoint vertices at x and z. This is nothing but dx comma z, and this is similarly this is z comma y. Now in geometry, what we know that sum of any two sides of a triangle, so sum of the lengths of any two sides of a triangle is greater than or equal to the length of the third side. So in particular, length of the side, this side is less or equal to length of sum of the lengths of these two sides. Okay, so this is less, this is so dx comma y is less than or equal to sum of these two lengths. Okay, so that is dx comma y is less or equal to dx comma z. So this is less or equal to this distance plus this distance. Okay, so this is so-called triangle inequality. So the first axiom is known as positive definiteness. Positive and this is commutativity. Axiom 2, this is commutativity. And axiom 3, this is so-called triangle inequality. Triangle inequality. So basically what we can see that what is d? D basically the notion of distance. So d is a function, okay, with domain as x Cartesian product with itself, and this is real valued, and that satisfies these three axioms, and these three axioms are so-called axiom of distances. Okay, now we are ready to define the distance function. So now let us define distance functions formally. So here is the definition. This is the definition of distance functions. So let us define it. Let x be a non-empty set, so X is not equal to empty set, a function D with domain X Cartesian product with itself to set of all real numbers is called a distance function if it satisfies the following three axioms of distances. Following axioms. So axiom 1, this is so-called, so already you have written here, so let us write again. So the first axiom is positive definiteness. So this is, it says that dx comma y is greater than or equal to 0, and this happens for all x comma y. This order pair belongs to the domain of D, that is X Cartesian product with X with equality holds with D x comma y. This is equal to 0 if and only if X equal to y. And what is the second axiom? This is commutativity. So this quantity, this read as the distance of y from x, and when distance of y from x is equal to the distance of x from y, then this common quantity we say as the distance between this common quantity, we say as the distance between 2 points x and y. So this is called the distance between x and y. And okay, so the second axiom, this is commutativity. It says that dx comma y is equal to dy comma x. Dx comma y equal to dy comma x, and this happens for all x comma y. This order pair belongs to X Cartesian product with X. And the third axiom, this is known as triangle inequality. It says that dx comma y, this is less or equal to dx comma z plus dz comma y, and this happens for x comma y comma z belong to x. And now we have, so now we would like to give a few quick examples, and before that we have following remarks. So now we know what is distance function. What is a distance function? So a distance function d on x. So d is called distance function on x. So this is also known as a metric on x. Which measures distance between 2 points. So metric, so this is also known as metric on x, which measures distance between 2 points in the set x. And second remark, this is And this is, one can say, this is as a definition. So it says that if a function D defined on x cross x to set of all non-negative reals. So this is set of all non-negative reals. So if a function, this function satisfies conditions 2 and 3, but not necessarily first condition. So if a function satisfies these two conditions in the above definition, then such a function D is called a pseudometric. Then such a function D is called a pseudometric. Okay, so now we gave 3 quick examples. So first example is so D1 defined on R cross R to R defined by D1 of x comma y. This is equal to the function x minus y, the absolute value of this quantity. So D1 of xy is equal to the absolute value of x minus y. Then one can verify that D1 is a distance function on R. Then D1 is a distance function on R. So it's the set of all real numbers. Now, so let's give this is example 1, example 2, D. So D infinity defined on R2 cross R2 to set of all reals defined by D infinity. So a generic point in R2 looks like x1 comma y1, and so order pair x2 comma y2. So this is equal to maximum of x1 minus x2 comma y1 minus y2, absolute value of this. So this is defined by this is a distance function on R2. Now, in the third example, here we give an example of pseudometry. D from R2 cross R2 to set up all reals defined by D of x1 y1 comma x2 comma y2. So this is equal to the absolute value of x1 minus x2. So this is a pseudometry. So one can verify. So this is not a metric, it's a pseudometry. It's not a metric on R2, but a pseudometry on R2. Okay, so now we are ready to define metric spaces. So this is the second item. matrix spaces. So here is the definition. Let's change color. So here is the definition. A matrix space, a matrix space is a pair x comma d where x is a non-empty set, x is not equal to empty set, and d is a distance function on x. It's a distance function on x. And so this is matrix space. This pair is called a matrix space, and the set X is called the underlying space of the matrix space. Underlying space or underlying set of the matrix space x comma b, and this is called the metric of the matrix space x comma d, and the pair x comma d, this is called matrix space. So here we have two examples. So x comma d, that is, so already we have given, so here we have given this examples of distance functions here. So r comma d1, where this d1 is defined here. So this is a matrix space. And also, a second, r2 comma d infinity. So this is also a metric space, and here, so this is metric on R2. So d infinity is a metric. Is a metric on R2, and this R2 is underlying set of this metric space. Okay, so, and this pair is called a metric space. So now we stop here.